Hey, AP Calculus, this is lesson 4.4. It's the first of several related rates videos. So I'm not going to go over the whole idea of related rates as I did in the first example with just x's and y's, dy dt's, dx dt's, but I am going to go over some of those actual application type problems. So I'm going to redo this ladder problem, redo most of the cone problem, and then we'll see where we're at from there. So, first example. We got a word problem. A ladder 20 feet long leans against a vertical building. The bottom of the ladder slides away from the building horizontally, and it gives us a rate of 2 feet per second. How fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? So, if we go off to the side here and say, here's our vertical building, okay? It can just be a vertical line like that. We've got our ladder leaning against the building, okay? So here's a little visual. We've got a 90-degree angle connecting the horizon, the horizontal ground, with the vertical building. And what we've got here is a 20-foot long ladder. It's always 20 feet no matter how far it slides away. But what we have for the other two sides of this, what appears to be a right triangle that will always stay a right triangle, is a vertical distance which changes. So I'm going to make it variable. Y usually indicates up and down, and then X usually indicates left and right. So what you're doing with related rates is you're saying, I want to create a primary equation that relates all the variables that are necessary, couldn't think of words there, so that when we take the derivative, we can potentially deal with rates of change that the problem is asking for. So we know that the horizontal sliding is going to be 2 feet per second that way, okay? So this 2 feet per second is making x a longer rate. So it's basically saying the rate at which x changes with respect to time, so the more time it spends sliding away, the larger the x unit will be, is going to be 2. How fast is the ladder sliding down the building? We don't know. That's the unknown. And then we're given a specific instant by which we are computing things. So 12 feet above the ground, that's going to be our y value. So the primary equation, something that relates all three sides of a right triangle, Pythagorean theorem. A squared plus b squared equals c squared, where a and b are the legs of the right triangle and c is the hypotenuse. So y squared plus x squared is equal to 20 squared. That equation holds. We know it's true. We want to solve for dy dt, which means we have to take the derivative of both sides of this equation with respect to t. Okay? And then when you take derivative of y, you get a dy dt out of that. When you take the derivative of an x term, you get a dx dt out of that one. So I think we've got something that we can move forward with. So what I'm going to do is give us some room over here off to the side to really explore the space. I don't think this is working out. Let's get rid of this marker. So I'm going to take the derivative of all of this with respect to time. So that's going to be 2y dy dt plus 2x dx dt. And then when you take the derivative of 20 squared with respect to t, that's a constant. It's going to zero itself out. Now you guys are going to be seeing the Pythagorean theorem more than just once or twice here. You're going to see it quite a bit. So you're always going to get the 2y plus 2x or the 2c on the other side. Dividing by 2 is an easy way to just make numbers reduce to nothing almost. So divide by 2, divide by 2, divide by 2, you get y dy dt. It's just a quick simplification technique that has nothing to do with the new less than. And now we can start to plug things in. The y value we know is 12. When the ladder is 12 feet above the ground. So the y value is 12. The dy dt, that's the unknown. We don't know what it is. The x value isn't explicitly given either. However, we know at the instant that the ladder is 20 units, the height is 12 units. We can use our primary equation to determine what that unknown value x is. So we go back to our Pythagorean theorem, plug in 12 for y, and then solve for x. So 12 squared plus x squared equals 20 squared. Now if we subtract 12 squared from both sides and square root both sides, we find that x is equal to the square root of 20 squared minus 12 squared, which comes out to be exactly 16. Okay, so x equals 16, and we know dx dt equals a positive 2, not negative 2, because we're increasing x. As this ladder slides down, x increases. So it's times a positive 2. Then we just do some algebra to get dy dt by itself. Minus 32 divide by 12. At which point you can simplify that fraction, divide the top by 4, the bottom by 4, and that comes out to be negative 8/3. So, interpret this solution. How fast is the ladder moving down the building, at least the top of it, when it's 12 feet above? It's 8 feet per every 3 seconds. That's how fast it's moving. Okay, example 2. A water tank has the shape of an inverted right circular cone of altitude 12 feet. If you can't read this, go to page 156. I can try to zoom this thing in. All right, that was pretty successful. All right, it's really zoomed in now. So here's my second example. Give you guys a second to read it. All right, this one's a little more complex. All right, what we're trying to do is determine the rate at which the water level is rising when the water is 3 feet deep. So usually when you guys see things like rising, we're thinking a dy dt, or in this case, we're talking about a right circular cone, which has a formula 1/3 pi r squared h as its volume. You'll see why I'm using volume in a second. So dH dt is sort of like the aha. That's the thing we're trying to solve for. But at any rate, the thing that told me that we should be dealing with volume is the fact that they told us that water, which is a voluminous type of like unit to measure, it's being pumped into the tank. Approximate the rate at which the water level is rising, and it gave us cubic feet. So the cubic feet is sort of like volume. That's units cubed. So here's what I'm going to do. I'm going to start out with my primary equation. The volume of a right circular cone. I'll just say of a cone. All right, can you guys see all that? Yep. That volume is 1/3 pi r squared h. It's the third of a volume of a regular right cylinder. So, interesting. We're not going to get too much into that though. So, my primary equation, it's kind of iffy because I've got two different variables. I know I want dH dt, so if we can get rid of the r's, that would be great. So in order to do that, we need a secondary equation. The primary equation is the equation that we take the derivative of. So we're eventually going to do d dt of this, but we first need to get rid of that r. Get rid of r using a secondary equation. And here's how I'm looking at this. So here's the cone. Its altitude is 12 feet. So that's basically like the height of the cone from top to bottom. So that height is now 12. And it gave us a base radius of 6, so this is the base of the cone. And basically what you do here is, no matter what the height of this water is, so let's just arbitrarily point to this being a height, you create similar triangles, the little triangle in the cone and the big triangle in the cone, in which the ratio of the altitude to the, sorry, I'm being kind of goofy here, to the radius, okay? So altitude to the radius equals mini altitude to mini radius. So what we do is we come up with a proportion as a secondary equation that gives us r's and h's together. So 12 over 6. Big altitude over big radius is the same ratio as little altitude, which I'll call h, over little radius, which I'll call r. So this is saying that 2 over 1 should equal h over r, which means 2r equals 1h. And that's exactly what we need to get rid of the r there. To get rid of the r, I need to get r by itself and then input just h values right there. So get r by itself, divide both sides of this secondary equation by 2. R equals 1/2 h. So that r equals 1/2 h now allows us to take r out of the equation and plug in 1/2 h squared. I took the r out, I plugged in 1/2 h squared. So what does that give us? Well, when you square 1/2 h, you get 1/4 h squared. Which gives me 1 pi over 12 h cubed. So now what I have to do is take the derivative with respect to time of both sides of the equation. So this is going to be dv dt. Can you guys see that? All right, sorry, I'm kind of writing in the middle of all this text. I can do basically power rule. Bring the 3 down. 3 pi over 12 reduces to 1 pi over 4. Take 1 away from the h cubed, but then I have to do the dh dt. I got to multiply by dh dt. All right, at which point, let's just double checking so I don't mess this up. At this point, we say, well, can we plug in for h? Well, we know it's 3 feet deep. So that tells us that the h value should be 3. Do we know what dv dt is? Well, the rate at which the volume, the amount of water coming in is changing, is 10 gallons per minute. But they tell us that 1 gallon is 0.1337 feet cubed. So what you do is you say, take the 1 gallon times 10 of those, and you're going to get the feet cubed per minute rate that we want. See, we want volume, cubic feet per time. D volume, D time. So that's an easy fix for us. It's just 1.337. Actually, let me think about that. It's 10 gallons of water per minute times okay. Okay, so yeah, dv dt is going to be 1.337. Can you get dh dt by itself? This will be 9 pi over 4. If I multiply by the reciprocal, 9 pi divided by 4, the reciprocal is 4 over 9 pi. That gets rid of it here. dh dt becomes, I think we need a calculator here. All right, so 4 divided by, make sure the pi and the 9 are in parentheses next to each other, times 1.337. That gives me 0.198. Sorry, 0.189 feet per minute. All right. Let's all take a breath. That'll be the end of this first video for related rates number 1.